Oh, hey everyone. Sorry, I forgot you mentioned that you wanted me to do some examples. I was just doing some other work. All right, so let us do a couple of mathematics. So here's Mathematica. This is the professional version. I, as a faculty member, get. I hope you're getting the same one. I don't really know. And I'll work some of the examples I did in class, plus maybe one or two more. So let's see here. As usual, whenever you do anything, you want to define functions and use them later. And this is because, so you want to define the function, then integrate it, then differentiate it, because when you make a mistake, it's just a lot easier to fix. So here's one example I did in class, which was to define a function, and I've named it Planck. I'm not going to, if I hit enter, then I'm going to initiate a built-in function, and I don't want to do that. So I'm not going to let that happen. And this is the Planck distribution, which is a function of lambda, so I call it lam. And it is, let's see, so I used 8 pi, oops, I'm making a lot of mistakes, 8 times capital Pi. Again, anything that is a known mathematical entity, it's built in, and you need to make sure that you tell it that it knows what you're trying to do. Pi is very special in mathematics. You don't want to treat it like an unknown constant, like we do with h and the speed, Planck's constant and the speed of light. And this is just a bunch of stuff to Mathematica. And one of the things I'm always trying to get across, to whatever extent, is that constants, don't ever let constants blow your mind or distract you. They never really do anything. They're important. Don't not include them, but you don't have to let yourself get cross-eyed by their existence. So anyway, okay, 8 pi hc squared over lambda to the fifth times 1 over exponential. So that is obviously a math thing. So exp, and exponentials, functions have to use brackets. I want to use a parenthesis, but it's a bracket. Okay, h times c over lambda, k, the Boltzmann constant T, temperature, okay, minus 1, parenthesis, and that is a mistake, actually. I need to, so it's 1 over e to the blah 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 minus 1. So I need 2 parentheses. There we go. And that's it. So I close bracket. No, I don't actually. I just hit shift enter. And is that right? I don't like it how it formats things, but that 8 pi hc squared e to the blah 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 minus 1 lambda to the fifth. So that's correct. All right, now we're going to integrate it. Okay, so obviously it knows what integration is, so we remember capital. We're going to, so integration is like a function, so it gets a bracket. I need to tell it to use Planck. Now you always, when you define a function, you still want to define what the variable is. I mean, I did tell it was lambda, but I guess you just need to tell it again. So I'm integrating lambda. Now this is very specialized syntax, and you have to get this right. We're going to define, it's a definite integral, so we need to define the limits. And you do that with a comma, curly bracket. I mean, you see it. We're integrating lambda. Again, I guess you're telling it, I guess, for the third time that lambda is the thing. We're going to integrate from 0, lower limit, to infinity. And again, we see that infinity is a known math thing, so we need to tell it that. Close with the curly bracket. Next thing is, you don't have to do this, but I suggest it. You need to give it some information about all these constants. If the constants are imaginary or negative, it could completely change the result. Okay, so assumptions, I've got several, so I'm going to use a curly bracket. If I only have one assumption, you just type it in. But if you have multiple assumptions, you need a curly bracket, such as the speed of light is greater than 0, because it doesn't know that. Planck's constant is greater than 0. Temperature will be greater than 0. There's no negative temperatures. K, the Boltzmann constant, is greater than 0. Remember, it has no idea what these things are. Okay. Curly bracket, and then the active integration requires a one last bracket to say this is the entire command. Shift enter to execute the command, and it takes its time, but there you go. That is the exact result. So now you can see why, if there's a slip of the finger, you want to use a defined function and then integrate that function, because when there's a problem, and again, syntax is what's going to get you. It can take forever before you realize you forgot to capitalize exp. I've been hung up on hours on this. Okay, an example related to your homework, which I did in class. Let's define a wave function. Let's have it defined with respect to r. So I'm doing this slightly differently than I did in class. Let us, I'm looking at my notes, equal, okay, it is 2 over pi to the power of 1/4. I may not need to use all these parentheses, but I get a little paranoid. Okay, it's an exponential minus r. It's minus r squared. Okay, and there's another exponential. Actually, I shouldn't be using r. I should be using x. It doesn't matter. I just am more comfortable with x. Okay, so this is a traveling wave. Okay, now we have the square root of -1, which is imaginary I. Now there's a shortcut to this, which is escape II escape. Escape II escape. Or you can type square root of -1, which is what I did in class. Okay, so you see me doing that. All right, I think that's it. So I hit Shift Enter, and that looks fine, I guess. Let's see if it is normalized. So now this is some quantum mechanics, specifics to quantum mechanics. We haven't covered this yet. We're just learning how to integrate things. Now, because I know quantum mechanics, I know that I want to integrate the conjugate, which is where, again, that is a no math thing, which is where all the imaginary i's are turned into minus i's. Now the reason I'm interested in multiplying the conjugate times the wave function, non-conjugate, just the wave function, is because this is a thing in quantum mechanics, and I'm going to integrate from x. I'm integrating x from minus infinity to infinity. Curly bracket. Then let's do some assumptions. There's always going to be some assumptions. Let's see, I need k is greater than 0. I don't think it actually has to be, but I'm just going to tell it is. Not a curly bracket. Okay, now what I was looking for here, it's a quantum mechanical thing that the conjugate of a function times itself integrated is 1. It's a probability distribution, so I'm just checking that. Okay, here's the other example I gave in class, which is to know the momentum of this wave function, which describes like a beam of electrons. It is the integration of the conjugate of the wave function times a constant, which is h over the imaginary I, escape II escape, times the derivative. Okay, so now here is an integration. Here is a calculus thing embedded in another calculus thing, and here's how you do it. D is a derivative, so we treat it like an integral. It's not an integral, it's a derivative. The derivative begins with a regular bracket. You then say what you're taking the derivative of and what that's a function of. And then you want to make sure that it understands that we are, in fact, taking the derivative of the wave function, which is a function of x with respect to x. So there seems to be a lot of redundancy with saying, okay, x, 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 r, 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 blah, blah, blah. Anyway. Okay, so there's in bracket. No, have I done something wrong? Oh, no. So I need an in bracket for the derivative. There we go. And that's it. I think. So you notice I'm close to losing track of my brackets. I'm a little confused. I'll just see whether it runs. Tell you what, let's make a mistake on purpose. Okay, let's. So I've made a mistake, but I made a mistake on purpose. Sorry. So let's integrate x from minus infinity. Again, it recognizes pretty quickly what I'm trying to do, and let us give it assumptions. Notice that it's clearly having a little problem here because I've not done this correctly. And so now I end here. I'm going to try this, and it's just not done anything, okay, because obviously I've messed up. So anyway, that's what a mess up looks like, and you know that I messed up by not putting an in bracket here. Okay, so now it seems okay, although this part is screwed up. So let me just go back here. Okay, now you see how it's behaving better? There's only one assumption, that k is greater than 0, k of the function, right? There's nothing else in there. And hk. Okay, now I happen to know enough quantum mechanics, I can tell you that is in fact the answer. Tell you what, how about we do one more? I didn't do this in class. Let's define a new wave function with respect to R1, which is going to be, let us make this negative r times r over r squared. No, r over a. Let's say it's r over a. A is a constant. Let's call it a0. I guess that's all I want, right? So I'm going to do that. Okay, now I'm going to integrate it. Now remember how I was saying how the conjugate of a function times the function needs to be, oh, why was it complaining? Oh, okay. Needs to be 1, so I'm checking whether this is normalized properly. R1 goes from 0 to infinity. There's no negative r's, right? Radii cannot be negative. In bracket, and the assumption are that a0, which is a constant, it's about half a nanometer, is not negative or imaginary. Oh, what did I do wrong? What did I do wrong? Oh, you know what I did wrong? It's a radial. 4 pi. I forgot the Jacobian. R1 times R1. 4 pi r squared. I forgot 4 pi r squared. Isn't that funny? Okay, I go back here. See what I did here? See what I did here? I said this is a function of R1, but there's no R1. I wrote R. Okay? Okay, now that I've fixed the function, I come back here. I have to put my cursor right there. Now I'm going to hit Shift Enter again. And look at that. Okay. Now let me redefine this. I'm going to copy and paste. And I'm going to say 1 over a0, a0 over pi. Okay. So I'm redefining this. Okay, then I'm going to cut and paste this again. Control C, Control V. All right, so that still works. Ooh. Oh, you know what I did? Now, again, I'm sorry, this is a lot of quantum mechanics that I know you guys don't know. So, this probably doesn't make a lot of sense to you, but I did something wrong, which was I'm supposed to normalize with the square root of the constant. So again, that's some specialized knowledge. That's the reason why it didn't integrate to 1. Okay. Now what the hell? Damn it, I did this right. 4 pi r squared. One over what did I do wrong here? See, this is supposed to be 1. Wait a minute. It is 1. Pi over pi? Pi over pi is 1. Oh, that's idiocy. Okay, so it is 1. It is properly integrated. All right. All right, that was stupid. I've never seen it do that before. Okay, well, that's a weird Mathematica thing. All right, anyway, so notice that I was trying to do something here. Now, I'm sorry, it may not be that easy to follow because there's some quantum mechanics, but what you did get to see me do was make a lot of mistakes, and again, the kind of mistakes that you're probably making that are probably frustrating. Tell you what, let's do one more example, also related to what you're doing. Let's integrate x, the function x, so we're going to tell it we're integrating the function x. The partial is x. We're going to integrate from 0 to 1. No, wait. X times, here's what I want to do. I want to do a double integral. So this is kind of related to the hard problem on your current homework. And I'm going to integrate y, the function y, and I'm going to integrate the y with respect to itself from 0 to x. So again, this is actually similar to what you're doing in your problem in bracket. Okay, and I'm integrating x. Actually, let's see, if I do an indefinite integral, I just won't give it any limits, right? A definite integral has limits, an indefinite one does not. Okay, is that all I need to do? No. Hold on one second. What did I do wrong? I guess I need to tell it integrate with respect to x, even though I'm not giving it limits. Yeah, look at that. Okay. Now you see why this worked? Let's see what this does. So we had an integral and then inside an integral. So let's copy and paste. Let's see if why this makes sense. Okay, so we integrated y, which is 1/2 y squared from 0 to x. So the result is x squared over 2. So that is the inner integral. And so the outer integral was actually integrating x times x over 2. We were integrating with respect to x from 0. Just integrating with respect to x. And right, the integral of x cubed over 2 is x to the 4th over 8, because the derivative of x to the 4th, and notice how crudely I do that, over 8 with respect to x. Remember, d's derivative is x, right, is our integrand. All right, hopefully this hasn't been overwhelming. I actually do like to make mistakes because that's shows you what you're probably doing wrong. And next time we do this, we're going to do some MATLAB. And anyway, I hope that's on your homework, and I will see you all on Thursday.